Hi, folks. We're going to keep pushing on with this chapter. There's really one major topic left, and this is a really kind of a cool result. It's called the Chinese remainder theorem. A lot of people will say CRT, and if you're talking about math and somebody says CRT, they mean this. Oops. The name is because this was first studied in China quite a long time ago, probably about 600 BC. And it came from a puzzle originally. So you have a bunch of men. I'm going to make a simplified version of it. Suppose you line men up in ranks of 5. I think it's supposed to be soldiers. So you know, line them up 5 abreast, and there's a certain number of rows, but then there's some left over. Suppose we line up our men in rows of 5, and we get 2 left over. And then we similarly, suppose we line them up in rows of 7. Can I just do we line up men in rows of 7, and there's 1 left over. Well, how many men did we have? Can you tell from this information? And you can only tell partly. You can tell how many men there are. Well, I don't know if up to a limit. But let me put it this way: if we found a solution of this, and then we added a multiple of 5 to it, it would still satisfy the thing of 5. In other words, we'd add some number of rows of size 5. And if we added a multiple of 7 to it, it would still satisfy this one. There'd still be 7 left over. Well, what if we added a multiple of 5 and 7 to it? It would satisfy both. Both remainders here would remain the same. And that's sort of the trick, actually. What this is talking about really is mod 5 arithmetic. This 2 left over is the number is 2 mod 5, and the 1 left over thing is that we're talking about 1 mod 7. The Chinese remainder theorem says, well, you can get a solution mod the product of these, mod 35. So adding a multiple of 35 to it will get you another solution, but the smallest solution is usually what people are interested in. I wonder if we can actually just guess and check at this. Multiples, we're looking for multiples of 5 plus 2, so things like 7 and 12 and 17, things like that, that happen to be 1 greater than a multiple of 7. And I think I just guessed at it. Is 21 a multiple of 7, right? And the 1 extra makes it 22, and that's 24 times 5 plus 2. Yeah. I'm sitting here babbling instead of writing it down. Sorry. 3 times 7 plus 1, that's 22. And 4 times 5 plus 2 is also 22. Just noticing those things. But this is a number that's 1 mod 7, and this is a number that's 2 mod 5. So it satisfies these conditions. If you had 22 people, you could get this to happen. Lay them out in rows of 5, you'll have 2 left over. Pointing at the wrong one. 4 rows of 5 with 2 left over. Rows of 7, 3 of them with 1 left over. All right, so the textbook takes an approach to this that immediately jumps into the harder case where there's more than just 2 things. I think I'd like to show you an example of, well, I think I'll do an even smaller one than 5 and 7. but sticking with just 2 different moduli first, and then we'll jump to the 3 moduli or more. So let me, instead of writing it in the silly word problems sense that the original was in, let's make it modern. Suppose we're looking for a solution to a system of congruents. I guess I should write for you, the general case is you're going to have maybe k different congruences with different moduli, and you're going to have something like x is supposed to be congruent to some first number modulo a first modulus, and it's going to be congruent to some second number, a 2 modulo some other modulus, m2, and so on down the line, let's say dot dot dot, until finally we arrive at x is congruent to a sub k modulo m sub k. But that's a system of congruences. I just want to deal with the easy case where there's 2 of these things. And to make it small enough for us to handle by hand, I'm going to make m1 be 3 and m2 be 5. Okay. But the general case is what we're aiming for. I just want to do the simple case, or a simple case first. And because we can do this case by brute force, essentially. So here's the actual system I want to look at. X is congruent to 2 mod 3. And x is going to be congruent to 3 mod 5. So I'm not sure how to motivate this for you, but I'm going to write numbers into a 3x5 table. So let's see, that table may not be big enough. Let's make it 3 this way. Can I divide that up into 5 even spots? That's close enough, I think. All right. And the reason I've made it a 3x5 table, it will become clear, I think, but the columns are going to be our values mod 5. Values mod 5 go 0, 1, 2, 3, and 4. And the rows are going to be our values mod 3, 0, 1, and 2. And here's a thing that's probably pretty obvious. If the smallest number that's 0 mod 5 and also 0 mod 3 is 0 itself. How about the smallest number that's 1 modulo both of them? Well, that's 1. So those 2 observations lead you to think, well, where would numbers lay if I just sort of counted up? I mean, where does 2 land? 2 is going to be 2 mod 3, and it's also going to be 2 mod 5, so 2 is here. Where's 3? Oh, now it just got hard. 3 is still 3 mod 5. 3 and 3 are the same, right? But 3 isn't on the mod clock if we're doing mod 3. Well, it's because it would be 0. So 3 goes here. Now that might be enough evidence for you to see the sort of general pattern that's going on. This is what I call the video game topology. If you go off the bottom of the table, you come back in on the top, right? And let's keep going like that. If we hit a boundary, we're going to just jump to the other side and keep going. So here's 3, there's 4. We go off the edge, and 5 comes in there. And now we go off the bottom, and 6 is here. 7, 8, 9, 10, 11, 12, 13, 14. Now, if I kept going that way on the diagonal, I go off the side and the bottom, and I come back in up here. So what I just did is write the numbers from 0 to 14 in a table so that you know what their values are, both mod 5 and mod 3. So if you want to solve this, you just go, all right, fine, where is the number that's in the second row and the third column? There it is, 8. So 8 is a simultaneous solution to something that's 2 mod 3 and 3 mod 5. Make sense? Now, if this was bigger, we wouldn't want to have to write out all the stuff. So we can, though, take advantage of some pretty cool stuff. The numbers right here, 6 and 10, are very special numbers in this setting. What's the point of 6? Well, it's 0 mod 3, but it's 1 mod 5. So if you sort of turn that 6 into a vector, or think of it as a vector, it's the vector 0, 1. And what's the 10? 10 is 1, 0, or it's similar to it anyway. And what kind of vectors am I talking about here? The first numbers are what our value is mod 3, and the second numbers are what our value is mod 5. I hope I just did that right. I could have messed up the order. Let's see, 6 is 0 mod 3, 1 mod 5, that's right. And 10, it's reverse. Why pick on those things? Because if I want something to be, what was the original question? 2 mod 3 and 3 mod 5. The unknown thing that I'm seeking corresponds to the vector, which was it again? 2, comma 3. Now tell me, if most of you have had some experience with vectors, what multiples of these two things would give you that thing? If you were thinking of them as vectors, you'd go, well, what we want then is 2 times 1, 0 plus 3 times 0, 1. Now, I'm not sure that you really need to think of them as vectors, so you can just replace these weird vector things I noticed with the numbers 6 and 10. If you did 2 times 6 plus 3 times 10, it's got the same effect. If you keep track of things mod 3, that's 0. If you keep track of things mod 5, that's 0. If you keep track of things mod 5, this one's 1. And if you keep track of things mod 3, that one's 1. So these two numbers are sort of are cool because they are 0 mod one of the moduli and they're 1 mod the other. It lets us build a solution. Just multiply by 2 and 3 respectively. Now what is this really? That's 30 plus 12. This is 42. But we're in a mod 15 world, right? I got 8 before. This doesn't seem to be 8. Have I just found the one that's at 2, 3? No, there is no 2, 3. Oh, yeah, 2. No? Yes, I gave the wrong, I'm sorry, I gave the wrong coefficients. I wanted to make it 3 mod 5. So I don't want to multiply that one by 3. In fact, let me just illustrate. We've got a sort of an instructive screw up here. We really wanted these things switched. I want to multiply 3, the value we're after mod 5, times the one that's 1 mod 5. And I want to multiply the 2 which is the value we're after mod 3, times the one that's 1 mod 3. And I've just got these reversed. Darn. I was sort of happy that it came out to be 42, but it won't be now. If we do that switch, I sort of owned up to my mistake by writing that, so let's just erase and fix the error. We want 2 there and 3 there. Now that's 18 plus 20, 38. And if we're reducing things mod 15, it's 8. So in the general setting, what we're going to be after is finding numbers like the 6 and the 10 here that that have a particularly nice value modulo all the moduli. We want something that's 1 modulo one of them and 0 modulo all the others. And then we can use a number like that to sort of build up. It'll often be too big and then it has to be reduced, but still to build up something that satisfies all of the congruences involved. So let's bump this up by 1. We'll do 3 congruences. This isn't going to be crazy big, but here it is, a system of 3 congruences. The moduli are 3, 5, and 7. So we actually, I can tell you in advance, in this case, we're expecting an answer modulo 105, the product of all 3 of those things. Let's say it in terms of congruence classes. If x is congruent to 1 mod 3, it's in the congruence class of 1. And that looks like, well, it's 1 and 4. I just keep bumping up by 3, right? So you should be able to think of all of these. 10, 13, 16, 19, 22. I guess I'm probably getting tired. I'm going to go to the end of the board and then we'll give that a rest. 25, 28, 31, 34, 37. It keeps rolling, but I only have to go up to 105 with that list. This is the congruence class that is 1 mod 3, so we'll put a little 3 subscript on this guy to let us know we're talking about that one. I also want the congruence class 2 mod 5. Well, that starts with 2, and then we add by, oh, look, there's a 7 and there's a 7. One way to think of this is we've just found something that's both 1 mod 3 and 2 mod 7. Said it wrong. 1 mod 3 and 2 mod 5. The number happens to be 7, which made my brain fail. Yeah, so that's interesting. That's a simultaneous solution of just the first 2 of these. It works. Interesting, but not where we need to be. Let's keep finding the rest of the elements of this congruence class. It's a matter of adding 5s. And oh, the pattern is nice when you're adding 5s in base 10 numbers anyway. To something that starts with a 2, the last digits are just going to alternate as 2s and 7s. So we'll have 17, then 22, then 27, then 32, 37, 42, 47. Have you seen another pair of things that are in both sets yet? I saw 7 and 7. 22 and 22. How far apart are those solutions? Looks like 15 units, and that's the modulus here. 3 times 5 is 15. Just thought I'd point that out along the way. 52, 57, etc. I guess 62 is enough. Now I also want to have to sort of list the things that are 3 mod 7. And And really what I'm now looking for is something that's in all three of these collections, all three of these sets. Oh, is there any nice pattern in the things that are 3 mod 7? I'm not seeing it. I think I just have to keep adding 7s. It's probably something I should have done on a computer, huh? 45, 52, 59, 66. Hmm. 73, 80. Have I found a spot yet where there's a number that's in all three of these? Is there any number that's in all three of them? Well, how about this? Can we find something that's in 1 mod 3, but it's in 0 mod 5 and 0 mod 7? Something that looks, honestly, as a vector, like 1, 0, 0? Because we can just look in this list and find the ones that are 0 mod 5. They're pretty obvious because they either end in 0 or 5. And 25, what else is going to be in 1 mod 3 but also be 0 mod 5? I guess we want to say something like this. This is made up notation, right? But I want to have a 1 in one slot and a 0 in the other if we're doing 3, 5 computations. So what do we get? 10 was 1 mod 3 and 0 mod 5. 25 was such a number, 2. How are those related? They're 15 apart, and that's because if you're expecting the same modular values to occur both mod 3 and mod 5, that'll happen if you bump up by 15. So we can actually think about the rest of the things in the set just by starting with 10 and adding 15 to each thing. Next one would be 40. Whoa, that's easy to see it's divisible by 5. Can you, why is this hard to write? Can you see that it's also 1 mod 3? Yeah, 39 is a multiple of 3, it's right before that. So 15 more would get us 55. 15 more after that would be 70. 15 more after that is 85. 15 more after that is 100. And if we go any higher than that, we're bigger than the modulus that we're after, the product of these things. 3 times 5 times 7 is 35 times 5, 105. So can you spot the one thing in here that is also 0 mod 7? Because that was what I was hoping to find. Something that's 1 mod 3, something 0 mod 5, and 0 mod 7. Well, it's actually pretty obvious, isn't it? That's the only one that's very clearly a multiple of 7. It'll be the only one. There's a unique solution to this kind of thing. Now, I don't mean to give you the impression that we have to do this by brute force, but I wanted to show you that even on a fairly large example, you can do it by brute force. So we found one of the numbers we need, 70. That's 1 mod 3, but it's 0 mod the other things. So I'm going to take that 70 and times it by 1. And that way I know I will have the right value mod 3. And it won't mess up this stuff. It'll be 0 mod 5, clearly. And it'll be 0 mod 7, also clearly. Great. Now we're like a third of the way there. We also want to find something that is 0 mod 3, 1 mod 5, and, or actually, I guess we can do it as 2 mod 5 if you like. Will that work? That'll work too. We can examine the things that are 2 mod 5 and look for the ones that are 0 mod 3 and 0 mod 7. Really? Where do we have 0 mod 3? Here's one. And there's one. I'm just scanning them. Here's one. And I thought 52 was, but it's not, is it? No. Wait a minute. What's the relationship? Where are these things that are 0 mod 3? How far apart are they? They have to do with the modulus of 3 and 5, together, which is 15. 15 and 12, 27. 27 and 15, 42. Where's the next one? 57. Oh yeah, I recognize that. I mean, being divisible by 3 is easy because you add the digits and you see. So, right, is there one of these ones that's 0 mod 3 and 2 mod 5, which is also 0 mod 7? Yep, there it is. So 42 is a number we're going to want. Actually, we could probably drop the timesing by 1. This number is 2 mod 5, but it's 0 mod 3 and it's 0 mod 7. Yeah? So this has no effect on these solutions, but it satisfies that one. Similarly, this guy, the 70, it was 1 mod 3, so it makes that one work, but it's 0 mod 5 and 0 mod 7, so it doesn't affect them. What if we add these two things up? We'll have something that for sure is 1 mod 3 and 2 mod 5. That would be, what is that, 112? Okay, it's past the size of our clock, so we'd get 7. That's cool. But it doesn't satisfy this one. So we need one more in fact, what 7 does, mod 7, is it's 0. And if you think about that, that happened by design. These guys both were 0 mod 7. So we need one more thing. We need something that satisfies this, that's 3 mod 7, but it's 0 mod these other two things. So the ones that are 0 mod 3 are the easy guys to pick on, so I'm going to do that again. I'm in the 3 mod 7 row. 0 mod 3, here's another 0 mod 3. There's a 0 mod 3. 0 mod 3 there again. That's off the edge of the board, but this might be enough. Is there one of these that's also 0 mod 5? That's the one we're after, right? We're 3 mod 7, but we want to be 0 mod 5 and 0 mod 3. Yeah, it's not so hard to spot. Right there, 45. So if I add up these three numbers, I'm guaranteed that it will be right modulo each of these moduli. Because this guy makes it be like 1, 0, 0. This guy makes it be like 0, 2, 0. And this one makes it be like 0, 0, 3. For each of the moduli, right? I hope that made a little bit of sense. So can we get this example to tell us something more accurately? Give us the actual. I mean, I was hoping to get you to see the pattern of how you think about the Chinese remainder theorem. Let's try to actually get a hardcore answer. I want to try to follow the notation of the way this is explained in the book pretty closely, because I'm going to do another example with, again, 3 things, but sort of do it in the abstract. And then we'll try it one final time where we'll have the full generality that there could be a large number of congruences to be solved. So let's suppose the first congruence is x is congruent to A1 mod N1. The second one is x is congruent to A2 mod N2. And the third congruence is congruent to A3 mod n3. So we'll stop at that. Now, for each I here, I1, 2, and 3, we're going to calculate a modulus that works for things relative to the other two moduli. That is, if I'm thinking about the first position, I want something that is a modulus that deals with the second and third positions. That number is called C something. So C1, in this case, that's going to be N2 times N3. And C2, these C's probably stand for complements because we're really thinking about a product of all three of these numbers, and this is that's the part of that product that doesn't involve N1. C2 would be N1 times N3, and C3 is, well, N1 times N2. In the text, they would write these things slightly differently. I'll just give you one example. This C3 would be N divided by N3, where N is the product of all three numbers, N1, N2, and 3. Now, why those C's? Well, we're going to solve for their inverses. We're going to find modular inverses for the C's. And we're going to do that modulo the modulus that's the same index. So I want C1's inverse mod N1 and C2's inverse mod N2. I just want to give that a name, and the name they give it in the book is D1, so we'll use the same thing. We'll say D1 is defined to be the inverse of C1 mod N1. D2, same thing, but the second position. D2 is C2's inverse mod N2. And I'm running out of space. Let me write really tiny. D3's equal to C3 inverse mod N3. Just barely fits. Okay. So why? Why do we do that? Because these numbers, the D's and the C's and the A's, give us exactly the right stuff to build a number that solves these congruences. So let me write it for you. Write A1 C1 D1 plus A2 C2 D2 plus A3 C3 D3. Why do we want that particular thing? Well, let's look at it mod N1. Mod N1, C1 and D1 are inverses mod N1, so that's a 1 in the modular arithmetic. And so the value of this thing is A1 rather, modulo N1. Similarly, this guy is A2 modulo N2 because those guys multiply to 1 in the N2 arithmetic, and that one's A3 mod N3. So these terms have the right values mod N1, N2, and N3 respectively. But look what they are mod the other things. Like when I'm looking at the first one, it has A1 in it. It also has C1 in it. And where did C1 come from? Well, gosh, it involved N2 times N3. Yeah? So this guy is A1 modulo N1, but it's 0 mod the other things. Just because of the C1. The A1 and the D1 don't do anything about it, but C1 being a multiple of N2 and a multiple of N3 means this whole term is 0 mod both of those amounts, both of those moduli. Similar trick here, C2 is divisible by n1 and n3, so this whole term is 0 mod the 1 and the 3 moduli, but it's A2 modulo the n2 moduli, and the thing works out just perfectly. This thing, you can build it, it's just sort of automatically gives you a number that is a solution to this equation, or the set of congruences. The solution, though, has to be taken in modular arithmetic as well. So what is the modulus that we would reduce this to? It's mod n, capital N, which was, I set it up here once before and I erased it. The product of all three numbers. So n1, n2, and n3. Let's just actually write it. N equals that. Well, actually, I'm wondering if we need to do the full generality. You probably see where it goes from here. If you had k things, you're going to get a1 through ak. There's going to be a similar definition of c1 through ck. It would be more like, rather than try to write them all out because you don't know how many there are, you'd write something like n divided by n1 here, and n divided by n2 there, and n divided by n3 there, and so on. That you can continue. Where again, n is the product of all of them, not just three of them, but if there's k of them. You want to take, I think we should do a slow notching up of the difficulty of our example. So this one I worked in generality. Let's actually try to put real numbers in it for our case where we've got 4 moduli. So how about x congruent to 2 mod 3? X congruent to 1 mod 4. X congruent to 3 mod 5. And x congruent to, let's go 1 mod 7. Right, so these are the A's, A1, A2, A3, A4. These are the N's, N1, N2, N3, N4. Our capital N is the product of those little n's, so it would be 3 times 4 times 5 times 7. Well, that's 20 times 21, 420. Can you see what the C's would be? C1 would be 420 divided by 3, so it would be 4 times 5 times 7, 20 times 7, 210, yeah. C2 would be, take this 420 and divide it by 4, 105. Did I do that right? 35, yep, 105. C3, that would be this 420 divided by 5, or maybe it's easier to just do 12 times 7, 84. And finally, C4 is, what am I doing now? 3 times 4 times 5, 60. Now, it's going to take a little bit of work to find modular inverses for these things, but not as much as you might think, because I can reduce these CI's down to the size of the modulus, or smaller. I can find them remainder-sized values of them. So C1 there, if we work it out mod 3, I think it's divisible by 3. Did I do something wrong? 20 times 7. Yeah, I certainly did something wrong. 20 times 7 would be, or 420 divided by 3. I see, I divided 420 by 2. That was bad. That was the wrong number in there. I hope the rest of them aren't messed up. Let's see. But this should have been 140. Yeah, different. It's either, well, actually the trick with the adding the digits works in modular arithmetic too. So if you add the digits of this, you get 5, which is 2 mod 3. This guy's congruent to 2. This guy is 1 greater than a multiple of 4, because 104 is fairly obviously a multiple of 4, so that one's 1. 84 mod 5, that's congruent to 4 mod 5, which is minus 1 in mod 5 arithmetic. And 60 mod 7, I believe that is 4. Isn't 56 a multiple of 7? Yeah. So what are the D's? Let me just make a column for DI. We'll write them next to their corresponding CI's. What's the inverse of 2 mod 3? It's 2. 2 and 2 is 4. 2 times 2 is 4, which is 1 mod 3. The inverse of 1 is always itself. So D2 can be 1. The inverse of 4 mod 5 is 4. Actually, that's another minus 1, right? And this is the only one that's a little bit tough. What's the modular inverse of 4 mod 7? Not so bad, actually. You look for things that are 1 mod 7 and see if 4 goes into them. And the very first one you'll spot is 8. 8 is 1 greater than 7. And 8 is 4 times 2. So that's a 2. Okay? So I've got everything now. I've got the A's, A1, A2, A3, A4, the right-hand sides of the congruences. I got the C's, and I got the D's. We can just write down this crazy number. That's the solution. It is 2 times 2 times 2 plus 1 times 1 times 1. Oh, that's a freaky one. Plus I'm like getting a little weirded out that this is too easy. Like maybe I'm making a mistake, but we'll see. 3 times 4 times 4. And the last one is 1 times 4 times 2. Now this whole thing would be taken modulo 420. But I don't even think it's big enough to exceed the modulus. This is 8 plus 1 plus, okay, here's a little tougher. 12 times 4 is 48. Plus 8. 40, try to do this mentally. 48 and 8 is 56, 57, 65. Really? I don't think so. All right, so we have the A's, the C's, and the D's. Let's see if we can write down that sum of products that gives us the answer. A1 is 2, so 2. C1 is 140, and its modular inverse is 2, mod 3. Let's just compute first, and then I'll make some observations about these numbers. But then the next one would be 1 times 105 times 1. The one after that is 3 times 84 times 4. And lastly, 1 times 60 times 2. Let's see, 2 times 140 is 280, and another 2 times that would be 560, wouldn't it? You know, I'm sort of not trusting myself. Let's do that on a calculator. It's 4 times 140. Yep, 560, okay. And then that one's easy, it's 105. 12 times 84, let's do that. 1008. And lastly, that's 320. Now what do I want to observe about these numbers? Well, that they're each the correct value modulo the position we're in. The first one is 2 mod 3. You might be able to check that. If this is 2 mod 3, what should be a multiple of 3? The number 2 smaller than it. So it's 558. Add up the digits. Yeah. Okay. So that's 2 mod 3. Can you see that it is 0 mod 4? Well, yeah, there's a 2 and a 2 in its factorization. Is it 0 mod 5? Yeah, it ends in a 0. Is it 0 mod 7? 56 is 7 times 8, so this is 10 times that. Okay, so it's got this value mod 3, and it's 0 mod the other guys. 105 here. What's that doing? It must be 0 mod 3. You know, the digits add up to 6. It should be 1 mod 4. I spot that. 105 is 1 greater than 104. But it's clearly a multiple of 5, and not quite as clearly, but you can check. It's 21 times 7. Did I just do that wrong? I totally did that wrong. 70 plus 35. It's 15 times 7. Anyway, it's still a multiple of 7. 1008. Apparently it's 3 mod 5. Yeah, 1005 would be the multiple of 5, just smaller than that, and they differ by 3. But maybe I shouldn't have written it out. We can see its factored form tells us the other things. That 84 inches is 7 feet if you follow the English system of units. So that's divisible by 7. 12 inches to a foot, so it's divisible by 12, which catches both 3 and 4 together. Right? So that 84 takes care of all the other moduluses. That thing is 0 modulo the other guys, but it is 3 mod 5. And lastly, this, it's supposed to be 1 mod 7. You just have to check. Is 319 divisible by 7? Doesn't seem like it ought to be, but yeah, so it's not. 1 times 60 times 2. I can't multiply, that's my problem. I don't know where that came from. 1 times 60 times 2, that's just 120, not 320. Excuse me about that. 120 there. Hopefully some of you were screaming at your screens while you were watching this. Anyway, that is 1 greater than a multiple of 7. 119 I recognize as 70 plus 49 gets you to 119. All right, so 1 mod 7, but can you see that it's 0 mod 5, of course, and 0 mod 4, yep, and 0 mod 3, So this sum does the trick if we take things modulo 420. I guess I don't trust myself to add all these 3 and 4 digit numbers, so let's go 560 plus 105 plus 1008 plus 120. It's 1793, which is a solution, but it's bigger than our modulus. We should be working modulo 420. So we'll make a reduction. Divide by 420. Somebody told me there's a thing in the math menu that gets us this, but I'm not sure if I can find it. Yeah. Let me just click that and do it. 1793. The quick way I do it is divide by the modulus. You get a decimal number plus a fraction. Control to a decimal number plus a fraction. Just subtract away the whole number part, and then times that fraction by your base again. Times you get 113. We need to verify it one more time. 111 is 0 mod 3, so 113 is 2 mod 3. 112 is 0 mod 4, so 113 is 1 mod 4. 113 is pretty clearly 3 mod 5 because it ends in a 3. And it's 1 mod 7. Is 112 really a multiple of 7? It is 16 times 7. So 113 does the trick. Okay, I think that we've got a pretty clear statement of the Chinese remainder theorem, and we've illustrated how the process of the algorithm for solving such problems works. There's just one last thing to take note of. I did a little legerdemain here. I fooled you. The Chinese remainder theorem, in fact, does not always work. And there's an easy way to see it. Remember how we had to find the modular inverse of Ci mod Ni? Well, can you always do that? No, in fact, you can't. And so the Chinese remainder theorem can fail utterly in a scenario where these guys aren't like these particular guys, where they're relatively prime to one another. Notice how nobody has any factors in common with anybody else there. If there's factors in common, there are some solutions, but you have to take into account the common factors, much like we had to when solving just regular linear congruences. But I don't think we'll deal with that scenario. Let's just say, provided the moduli are all pairwise relatively prime, you can put any numbers in here as the right-hand sides and go through this process of finding the CIs, the modular inverses of the CIs, and forming that big sum of products, and you'll get an answer. You'll get a thing that solves the congruence. All right, so yeah, that's the end for today. I'll be getting this posted kind of late, unfortunately. It's probably going to be close to midnight on Wednesday, but I hope you'll be able to have a look anyway. It's a short video. I don't know why I'm talking to you like this right now, because if you're hearing my words, you've already watched it. Right. Bye.